Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 73. It's on resistors and capacitors. A resistor is drawn like this in a circuit diagram, and what it does is it restricts the flow of current in the circuit. A capacitor is drawn like this, and what it does is it stores charge in a circuit, and then it's not going to be a circuit unless we have some kind of an energy source. So we've got an EMF, or in this case, it's going to be a DC power source. So if we connect them like this, you should know not only what do the resistor and the capacitors do, but what makes a good resistor, what makes a good capacitor. And so to understand that, you really have to understand at the gut level how a circuit works. And analogies work best for this. And so we're going to use an analogy of water flow to explain how a circuit works. So the first thing you need is an energy source or electromotive force. In this case, I'll represent that with a water pump. So as you're pumping that water, the water we'll say is going to flow in this direction. It's going to go all the way around the circuit. Let's say it's in pipe, and then it's going to be drawn up into the pump again. And so what's the first thing we could measure? Well, we could measure the potential difference. I could put my hand here, and I could put my hand here, and I'd measure the potential difference between the two. There's going to be way more potential energy up here. And so if it's an electric circuit, we call that the voltage or the potential difference across that EMF. What's the other thing you could measure? We could measure how much water is actually flowing. And in electricity, we call that I, or current. So it's how much we know it's electrons that are moving through the circuit itself. So what's a resistor? A resistor is anything that we add to that circuit that's going to resist flow of current. We could restrict that in a water pipe by simply making the pipe smaller. It's harder for that current to flow. We're going to have a higher resistance. Now, what's a capacitor look like using this analogy? It's almost like a dam that obstructs the flow of that current. But imagine a dam where we have a rubber sheet that goes right across it. So as the current flows into it, it builds up a huge amount of potential energy. So there's charge there, but the current can't continue to flow. And so in a circuit, you should understand resistors and capacitors. Not only what they do, but how do you make a good resistor? How do you make a good capacitor? And so with a resistor, we want to increase the resistance. And so one way to do that is through the material it's made up of. And so if we have high resistivity, that's going to slow the movement of that current, and we're going to have a better resistor. But you could also build it in a different way. It could have different geometry. And so there's a direct relationship between the length of the resistor and the amount of resistance it offers. And then there's an indirect relationship between the cross-sectional area. So what does that mean? If we make our resistance longer, then we're going to have greater resistance. But if we make it wider, we're actually going to have less resistance. And so if you want a good resistor, we want high resistivity, we want a long resistor, and then we want a really narrow cross-sectional area. Now, how's a capacitor work? A capacitor is based on the material as well, but it's between the two plates of the capacitor itself. We call that the dielectric. And so the higher that dielectric constant is, the greater the capacitance of the capacitor is. But geometry affects it as well. And so the larger that cross-sectional area is, or the area of these two plates on either side, the greater the capacitance is. And then there's an indirect relationship between the separation between the plates. So the more narrow we make that gap, the greater the capacitance is going to be. Now, to measure the current that goes through a resistor, we simply use Ohm's law. So to figure out the current through a resistor, you simply divide the voltage, so the potential difference, divided by the resistance. And then on a capacitor, we're going to measure the charge that actually sits on the capacitor. And that's simply equal to the capacitance times the voltage inside the circuit itself. So let's start with resistors and resistance. And so I've got a simple circuit here. So I've got some batteries and a light bulb. You can see that the light bulb is not lit. And so that's because electrons are not able to flow through the circuit. So if I take something like gold and I put it in the middle, then electrons can flow. And so gold has a really low resistance. Let's add glass in the middle. Glass, nothing happens to the light bulb, and that's because it has high resistance. But then we could take something like carbon, put it in the middle, and it's going to have a resistance somewhere in the middle. And so a resistor is really put together to resist the flow of those electrons. And they have little bands on the side that tell you how much resistance there is and the precision of that resistor. But there are really three parts to a resistor. We're going to have the resistivity, what the material is made up of. We're also going to have the length of the resistor. And then finally, we're going to have the cross-sectional area. So now let's play with the resistance of a resistor. What I'm going to do is I'm going to increase the resistivity, what it's made up of, increase in resistance. And so there's a direct relationship there. Let's look at length. Increase length, more resistance. Decrease length, then we're going to have decreased resistance. That's because it's in the numerator. Now let's look at the area. As I decrease the area, greater resistance. As I increase the area, there's going to be less resistance. So you can think to yourself, how do I make the least resistant resistor? I'm going to want a really large cross-sectional area, small length, and small resistivity. You can see the resistance goes to 0 ohms at this point. What if I wanted to have the most resistance in a resistor? Then I'm going to do the opposite. High resistivity, I'm going to have a really long length, and I'm going to have a short resistance, so a really large, or a short cross-sectional area, so I'm going to have a really large resistance. And so you should be able to calculate the current across a resistor. And so this is a PHET simulation. I've got a battery here. You can see it's a 9-volt battery. I've got an ammeter down here, which is going to measure the amps or the current or I in this circuit. And then you can see that I have a resistor over here. In this case, we've got a 9 ohm resistor. Well, you can see here right away that this is a 9 voltage. So I could put 9 up here. What's the resistance? The resistance is going to be 9 ohms. And so I could put 9 right here. What's 9 divided by 9? I've got a current of 1 amp. And you can see that reads right there. But watch what happens when I start to change the ohms. As I increase the resistance, what's happening to my amps? It's cut in half. If I increase it again, 27 ohms, now I'm going to have way less amps. Less current is actually making it through. You can see as I change the resistance, make it greater, there's really low amps. As I decrease it, we're going to have high amps to the point where I really shorted out my battery and we've got a fire going on. Now let's move to the capacitor. A capacitor is 2 plates, and charge will start to build up on either side of it. So we get these electric field lines, and that's where the potential energy is. To increase the amount of capacitance, we put a dielectric in the middle. And so our equation for this is the dielectric constant, so that's going to be right here. Now this is the permittivity of just free space, so that's going to be a constant. Then we've got the area on the top, so that's the area, cross-sectional area. And then we're going to have the displacement on the numerator. And so that's going to be the distance between these two gaps. And so the 3 things you should understand, number 1 is the dielectric constant. So I'm going to, in this simulation, I'm going to take that dielectric and I'm going to slide it in between the capacitor. Now it has a dielectric constant of 1, but see what happens as I increase the dielectric constant with Teflon, paper, and glass. What's happening to the capacitance? It's increasing. So as I increase the dielectric constant, I'm increasing the capacitance. What happens as I decrease the separation between the two? I'm increasing the capacitance. And then what happens as I increase the cross-sectional area? I'm increasing the capacitance. Same thing. If I pull it apart, make it smaller, pull out the dielectric, I've gotten rid of that capacitance. Now you also should be able to calculate the charge across a capacitor. And that charge is simply equal to the capacitance of the capacitor times the voltage. And so now I've got a capacitor I've hooked up to a battery. As I decrease the voltage, charge goes down. As I increase the voltage, charge goes up. Watch what happens as I change the capacitance. There's going to be a direct relationship between the capacitance and the charge. And so all you do if you want to figure out the charge on a capacitor is you take the capacitance of the capacitor times the voltage, and that's going to tell you how much charge or how much Q can build up on that capacitor. And so did you learn to make predictions about how resistors and capacitors work in a circuit? Remember, resistors resist flow, capacitors store energy. Could you design a capacitor and a resistor that works best? Remember, it's made of what material it is and then the geometry of how it's put together. Could you analyze to figure out how changing the resistor or changing the capacitor could change the voltage and the current inside a circuit? I hope so, and I hope that was helpful.